Hi everyone. So we're gonna start on Steck section 7.6 today on practical considerations. So this is a continuation of how um, we have the idealized op amp and how it works, and then we can make a lot of predictions out of that. That these are real physical devices, and therefore last time we already talked about how high pass and low pass amplifier we have these non-ideal behaviors of the op amp, which is the input bias current and the input offset voltage, right, which gives you non-ideal performance on your amplifiers. There are more non-ideal behaviors of the op amps, but the book brings up a interesting example of a lower grade op amps, which we don't have in this in our lab. It's the LM741. Um, and this op amp has a very large input bias current. Let's see if I can find it here. Right, input bias current. So has a maximum of 500 nanoamp. Compare that to the LF411 that we use in the lab. It's about 2,500 times bigger, and this shows up in your amplifier because, right, if you use the LM741 instead, let's say in this inverting amplifier with R1 and R2, and let's say R1 is 10 kilo ohm and then R2 is 1 meg ohm, you typically don't want to use such a large feedback resistor because to constrain the current quite a bit. But right, but if you just do the ideal situation, right, you have a gain of negative 100 here from just this equation here, right? So if your input bias current, right, that means what that means is that these inputs are actually drawing current, right? 500 nanoamp, 500 nanoamp. Okay, in order to measure the voltage, right? This is the maximum number, so we're doing the worst case situation, right? This is drawn into both of the these are current that's being drawn from V in, but also from V out, right? So both of the current kind of comes in here, right? Remember that golden rule number 2 says they don't draw current, but these are not. We'll try to show you the case that where the op amp tries to do the golden rule but doesn't quite get there, right? So we have this 500 nanoamps of current that's being drawn into the inverting input here. Okay, so this input resistance, right? You can think about it as basically an R1 and R2 being drawn current together, so they are parallel. So if you put a big resistor with a little resistor parallel to each other, basically the input impedance just is about the little resistor, right? Because the current will actually follow the path that has low resistance. This create about a input voltage of about 5 milliamp. So 5 milliamp is not a big deal, but right, if you place such a large amplification on this, like 5 milliamp, right, if you multiply that by 100, right, this should be 0.5 volts. Okay, so you're going to get a half volt difference on the output because, right, you have this input bias current that you cannot get rid of because of the design of the manufacturing of your op amp. So if you replace the LM741 with our LF411, basically your maximum input bias current goes down to 200 picoamp, right? So the output difference will be 0.2 millivolts instead, right? So these are drastically different numbers. So half a volt you actually care about, right? 0.2 millivolts. Our scope would actually not even be able to tell the difference. There are solutions to this if you ever have to use a lower end amplifier, or right, you need output amplification that are more accurate than 0.2 millivolts, let's say. You can sort of deal with this a little bit by basically adding R1 and R2 in parallel, so you're just adding more resistor to your circuit. Because what this will do, right, because remember this input bias current is drawing current into here, and it's giving you this 5 millivolt at your inverting input, right, you can do the same thing here because the same amount of current will be drawn into, right, your non-inverting input, right, and that'll give you the same voltage between the two. So that way you're basically setting both of your non-inverting and inverting input at the same voltage, so therefore it doesn't amplify that. Okay. So I think there's a few more other examples that the book goes through, so I encourage you to read through that. But a lot of times the solution is just, if you need a better op amp, get a better op amp, right? This is another thing that happens. So instead of both input drawing the same amount of current, they could draw a different amount of current because one of the resistor in one channel, let's say the inverting input, right, has a slightly different impedance compared to your inverting input. Okay. So in that case, right, one input draws more current than the other. That's called an input offset current, right? This can be fixed by adjusting the input by having an input impedance matching offset. But that also depends on the temperature. So some op amp even has a little offset resistor you can add to it. But typically the best solution is to, once again, buy a better op amp. And the book goes through a couple of solutions for that also. The next thing we can look at is this common mode rejection ratio. Remember, these operational amplifiers are just differential amplifiers on overdrive, right? When we deal with differential amplifiers, right, we want the differential mode to get amplified a lot, and we want the common mode to be suppressed, right? And this is quantified by the gain of the differential mode divided by the gain of the common mode, right? And you want this number to be as big as possible, right? And that way, when there's some common voltage between the two, you don't amplify that. Okay. So let's see how this affects our inverting amplifier. Okay. So, right. So if V in plus, right, the non-inverting input and the inverting input, they're both at ground, right? So since this line is attached to here, right, and then we're not thinking that we're going to have input bias currents, right? We're just trying to tackle one problem at a time, right? The inverting input should also be 0, right? So the common mode between them are both 0. Okay. One is a real ground, the other one is a virtual ground, of course. Okay. So there's no common mode signal to amplify between the two. So the inputs, right, of both of these of the amplifier are both going to be 0 with a constant. Okay, so you're not going up and down. You're also not having like an offset up, offset down that the inverting the amplifier will amplify. Okay, so in this case, right, there's no common mode signal between them to amplify, and therefore this common mode rejection ratio doesn't actually matter. And this is the reason why you're going to see a lot of amplifier applications. They always do an inversion. When I was learning this stuff, like I was wondering, like, why do you keep inverting the thing? Just do a non-inverting amplifier, right? That way you don't have to deal with inversion over and over again. So this is the reason why, because, right, in case there is some common mode signal offset between them, you don't amplify that, which is really great. Okay. So what about the non-inverting amplifier? Hopefully I didn't give the story away. So when Vin, right, is tied, so V plus is tied to Vin, so whatever the voltage here is going to be whatever the signal is. I'm just going to draw it here, let's say, right? So like this, right? Okay. So at this point though, right, this is basically a voltage divider of V out, right? Whatever here is, right? There's also oscillation here. So any common mode noise, right, between them, if they're both shifted up or down, that would get amplified, right? Because V out is basically going to be whatever 1 plus R2 over R1 of V in, right? So if this gets shifted up by 0.1 volt, this gets shifted up by 0.1 volt, and all those actually get multiplied, right? Let's say your 1 plus R1 over R2 over R1 is 100. So you're amplifying that 0.01 volt, 0.1 volt, to 11 volts, right? So you actually, sorry, 10.1 volts. So you're actually making a huge difference. So this is the case where non-inverting amplifier, right, has both the differential and the common mode components in it. So therefore, right, it'll cause if your op amp has a low common mode rejection ratio, you start amplifying this common mode shift between the two inputs. Okay. So so both the differential and the common mode component travels through your operation amplifier. Okay. So non-inverting amplifier are highly susceptible to these common mode noise issues. So this is why when people build amplifier, they tend to make inverting amplifier all the time. Okay, so now let's talk about the power supply. As you see in the circuit diagrams, right, your op amp has to be powered by a V plus and a V minus. So in the lab manual, you're going to see this as VCC, and this may be VEE, right? But sometimes denoted negative VCC. Okay, depends on the nomenclature. There's all kinds of ways to denote this. Okay. For the LF411, they are designed, if I remember right, this has to be a minimum of like 1.5 volts, and then you can go up to 18 volt technically, but usually you stay away from that. You just go up to 15. This has to be minus 1.5 volts to minus 18 volts, right? So this makes it so that you always have to have a dual power supply, meaning something that can give you positive voltage and negative voltage relative to the ground you're using. Sometimes you can float the ground and get away with it, but then once you couple it with your scope probe or something like that, then the scope shares the ground with the power supply, and then that doesn't work, right? So these are known as dual supply or split supply op amps. There are single supply op amps such as the LM358, just to introduce you to them. So these are really nice, especially when you're using them on digital system, which is what we're going to cover the latter half of this semester. Having basically, you can power these from, let's just draw it again, right? Your VCC is going to be equal to 5 volts, and then basically you can just tie this other end to ground. Okay. You can tie them to negative voltage if you want, but you don't have to. That's the idea. So that and these are really nice for digital system, because a lot of digital systems actually don't have negative voltages. Okay. You can find these if you see something like this where it says supply voltage equals to Vs, and then it's the difference between V plus and V minus. So unfortunately, right, previously, right, they denoted, V plus and V minus means the inverting and non-inverting inputs, but in this case, they actually mean the voltage supply. Okay. Okay, there it goes. Recording. Okay, so yeah, so these LM358 can be powered with a single voltage power supply, and it's this really nice for digital system, because then you can just run it with 5 volts, and then the other goes to ground. And we're going to see why a lot of digital system works well on a single power supply as opposed to having to deal with a split or dual power supply, which is needed for the LM411 that we're using, for example. Okay. The nice thing about the single power supply op amp also is that you don't have to use them as single, right? There is a maximum difference between the two. You want it to be less than 40. So so you could power these this LM358, for example, with a plus or minus 10 volts if you wanted to, but you can just power it with 10 to 0 or 20 to 0 as you like. Okay, let's talk about a little bit about more power supply, because right, these power supplies are basically how is connected to the collector of the transistors inside your operation amplifier and the emitter in case of the split one. Okay, any kind of jitter, right, or noise in these power supply is going to could change the amount of current that it actually drives through the transistor, and therefore causing your output to be not what you expect it to be. And this is quantified if you look up the specifications by the book calls it power supply rejection ratio. I think if you actually look it up, it's actually listed a lot of time as supply voltage rejection ratio. And you want this number to be as big as possible, so 80 to 100 decibel. So that's going to be 10 to the 4 to 10 to the 5, right? So, and that will give you a substantial rejection in case there is a little glitch in your power supply, and therefore it doesn't affect your output because there's a slight glitch in your power supply. And the way the op-amp does this is by basically adding a little bit of capacitors inside your operational amplifier. And you can even enhance this if you want, right? Is to basically add capacitors to your power supply input. Okay, so the drawing here, right, you have the V plus here, VCC here. I'm just going to call it VCC, and VEE here. What you do is you add a capacitor parallel to ground, right, connect to the ground here, right, and therefore this little capacitor basically kind of acts as like a little buffer, because in case there is a little glitch in your power supply, right, this capacitor, right, continues to flow current into your in this case flow out of your op-amp, and therefore, right, it gives you a kind of a soft landing. It's, you know, depending on the size of the capacitor, it's not going to last forever, of course, but right, it buys you maybe like a nanosecond, where a lot of these power supply glitches, you know, may not last that long. Okay, so one thing to note is that when you have a small capacitor, it can respond very quickly, meaning if you have glitches that are, you know, like a few nanoseconds, right, a small capacitor is very nice for that. But larger capacitor has a longer decay time, meaning, you know, if something lasts for a millisecond, it can still supply your op-amp until that glitch goes away. But, right, a lot of times you have to balance between the two. You want something that responds fast, or you want something that lasts a long time, because the ones that last a long time may not respond fast enough to very short glitches. Okay. So another way to also extend this this capacitor delay, right, is basically adding a little resistance to your VCC and VEE. Okay, that basically kind of gives you like an RC decay, right? So, you know, this RC decay was like 10 ohm times 0.1 microfarad, right? So that gives you, well, 10 microseconds. So basically, you have, you know, something on the order of a few hundred nanoseconds for your power supply to pick back up before it decays. One thing that's not nice about this is that it does put a resistance on your power supply. So if you're drawing current through this, the more current you draw, right, it drops your power supply voltage. Okay, so so this is one solution. For critical components, what people actually do is that they have fast ceramic type of capacitor, which is what we tend to use in our class, and then they put a tantalum, which is the medium capacity capacitor, and then for a large capacitor they put a little electrolytic one, and these are of course polarized, so that's why you have to orient them the correct direction, right? That's what these tantalum and electrolytic power capacitors are made for, so it can stabilize the power supply voltages on your electronics. So you're going to see this a lot, especially for mission critical, where, you know, you want to deal with the fast noise in your power supply and also be able to last a long time in case there is a long glitch that, you know, takes something order of milliseconds to recover from. So that's section 7.4, and then next lecture we're going to do a little bit of finite gain analysis in 7.7. So see you there.